Good morning, good afternoon, and good evening to all of you who are currently watching this video. First of all, I would like to introduce myself. My name is Chu Li Zhuo and metric number A17KM0062 from School of Mechanical Engineering, University Technology, Malaysia. Before I start, I would like to express my gratitude towards the panels for spending your time to evaluate my work, and especially to my supervisor, Dr. Wan Famin, for guiding me in completing this undergraduate project one throughout this semester. So let's begin with my undergraduate project title, Cooling Slope Effects on Microstructure and Mechanical Properties of SG91D Magnesium Alloy made by Semi-Solid Processing. So what is AZ91D magnesium alloy? The 9 here stands for 9% of aluminium and the 1 here stands for 1% of zinc. The D is for cadmium in ASTM specification B275. It has unique mechanical and chemical properties which make it commonly used as a biomaterial. So as we all know, casting defect will reduce its mechanical properties, and through semi-solid metal processing, it will combine the advantages of both liquid metal casting and solid metal forging process. So cooling slope casting method is one of the most popular semi-solid metal processing due to its simplicity and cost-friendly. We do not have to purchase any expensive professional equipment to perform a cooling slope casting. And cooling slope parameters such as cooling slope angle, cooling slope length, and pouring temperature plays an important role on microstructure and mechanical properties. So the problem statement for this project is to make semi-solid SG91D magnesium alloy by cooling slope method, and the parameters that affect cooling slope process, especially on the microstructure and mechanical properties, and to find the best condition to process semi-solid SG91D magnesium alloy by cooling slope method. And the objectives of this project is to investigate the effect of cooling slope parameters on mechanical properties and microstructure of S-CAS magnesium alloys. And secondly, to investigate the solidification mechanism and growth rate kinetics with respect to the cooling slope parameters. And the scopes for this project is to review the effect of cooling slope system on microstructure change and mechanical properties of alloys, and investigate the effect of cooling slope system with various melting temperature, angle of slope, and boring distance, and perform microstructural investigation of S-CAS sample using an optical microscope, SEM, and elemental verification using EDX. And lastly, to investigate the mechanical properties of S-CAS sample using tensile and viscous hardness machine. And next is literature review. This is a paper from 2019. Figure 1 shows the schematic diagram of the cooling slope setup. And in this experiment, the slope angle is fixed at 60 degrees, and the pouring temperature varies from 640, 650, 660 degrees Celsius, and the slope length varies from 300, 400, and 500 millimeters. And undergoing microstructure analysis using optical microscope, we obtain the shape factor using this equation and the average grain size using this equation. So when shape factor equals to 1, it means a perfect circle. So what we're trying to do is try to make the shape factor approach to 1. And the A in this experiment is the area of the alpha phase, and the P stands for the perimeter of the alpha phase. And this is the graphical result. And by performing mechanical properties tests, we obtain Rheocast specimen will have higher yield strength and higher ultimate tensile strength and better elongation. And the second paper is from 2018, and this is the forming of globular structure with increasing shear, increasing time, and decreasing temperature. And before flow still have dendritic arms, and after flow the dendritic arms become globular structure. And semi-solid cast we have globular structure, and conventionally cast will have dendritic arms. And from figure 4, we can obviously see that the ultimate tensile strength, yield strength, and elongation is better for a semi-solid metal. And figure 5 shows the effect of the shape factor on the ultimate tensile strength and elongation. You can see when the shape factor is approaching 1, the ultimate tensile strength and elongation are the highest. And this figure shows the mechanism of the breaking down of dendritic arms into globular structure. So there's an optimum condition to produce the best microstructure and mechanical properties for semi-solid alloy. In this experiment, the best cooling slope length is 400 millimeters and the best pouring temperature is 650 degrees Celsius. And ultimate strength, tensile strength, and elongation improves as the shape factor approach 1, and not only due to the non-dendritic microstructure, but also due to the small size of primary alpha phase. And this is the mechanism of forming of globular structure. So under shear force, the dendritic arms bend plastically. The dendrite arms experience large misorientation and form dislocation. And lastly, these dendrite fragments act as nuclei, causing and leading to presence of globular structure of the primary phase. A paper from 2015 showing the at the bottom of the slope, the shape factor is closer to 1, and when the slope length is fixed at 250 and slope temperature and room temperature, the shape factor closest to 1 is at here, and varying the slope length and pouring temperature, the shape factor closest to 1 is here and here. And when varying the slope temperature and pouring temperature, the shape factor closest to 1 is at here. And this is to summarize the effect of pouring temperature, slope length, and slope temperature. When the pouring temperature is too high, the nuclei might dissolve back into the melt, hindering nucleation. So with longer slope length, the duration of contact increase, which account for large formation of number of nuclei. And the temperature tend to reduce further down the cooling slope and resulting in higher shear force, inducing formation of larger number of nuclei. And increasing in slope temperature decreases the cooling ability of the slope and reducing the chilling effect and reduce formation of nuclei. And molten at the end of the slope might remain at high temperature, and it tends to dissolve back into the fluid flow and fewer nuclei would survive. And the paper from 2015 has proven that SZ91D magnesium alloy will dissolve in human body, so indicating when a temporary implantation is required, we can use a SZ91D magnesium alloy, and the magnesium alloy will slowly dissolve in the human body, and no second operation is required to take out the temporary implantation. And this paper from 2014, in this experiment, the pouring temperature varies, cooling slope angle varies, and cooling slope length varies. And note that this shape factor equation is the same as the previous equation, and these are the results. So in this paper, the magnesium alloy possesses a fatigue strength of 70 megapixel in modified simulated body fluid, which is considerably lower than required, so indicating the need to use semi-solid processing method to enhance the material properties. So from the 2014 paper, the optimum condition to produce the semi-solid metal is 660 pouring temperature, cooling slopes 360 millimeters, slope angle 48 degree, and the isothermal holding time is 9 minutes. And this figure shows the experimental setup, and experiment 1, 2, 3, and 4 each has its own casting parameters, and the optimum casting condition will be discussed later in the literature comment section. And this is the box scouting method to find FD, and FD is fractal dimension. It's a quantified figure to describe irregular geometric structure. And this is the relation between FD and grain diameters and also shape factors. And this paper shows that the 60-degree slope angle produces sample with DOS, degree of sphericity, which is known as shape factor also, closer to 1 and smaller grain size. From the optical micrographs, we can see the formation of globular structure throughout the cooling slope. And the SEM micrographs can be used to observe surface fracture and flaws. From the 2013 paper, the best processing condition has been identified as 60-degree slope angle, 925 Kelvin pouring temperature, and 333 slope wall temperature. And similar to for the first paper, the equation used to calculate the shape factor and grain size are the same. This three figure shows the improvement of globular structure after certain process and change in shape factor of the grains with isothermal holding time. And this is the degeneration of the dendritic structure, growth of rosette, and this is nearly globular grains. And this paper is to compare the light microscopy and electron backscatter diffraction analysis. So cooling slope process will degenerate dendritic structure and finally form globular structure. And undergoing isothermal holding afterwards will improve the shape factor and becoming more globular. So, and EBSD has much higher resolution compared to optical microscopy technique. Using EBSD will have higher accuracy. However, the sample preparation process is very crucial. So from the papers that I have reviewed, all of them are using optical microscopy instead of EBSD, so indicating optical microscopy should be sufficient to determine the grain size and globularity of the cooling slope metal. And this paper has shown that the corrosion rate for semi-solid process SZ91D has much lower corrosion rate compared to the die-cast SZ91D. The XRT pattern evidence the presence of two solid grid solutions by a slight shift of the peaks at higher delta theta values. This is the general physical properties of SZ91D that are obtained from GMAT Pro software. And this is the process that I have designed using these parameters and undergo microstructure investigation and mechanical tests. This is the microstructure investigation sample preparation. This is to perform the mechanical strength test. And the expected outcome is the different experimental parameters produces different microstructure in terms of globularity and grain size. And I predict that 640 degrees Celsius pouring temperature, 45 degrees slope angle, and 400 millimeters cooling slope length will produce SZ91D magnesium alloy with the best mechanical properties. The reference and appendix. Okay, thank you very much. That's all from me. Thank you.